Welcome to the lecture series on alkyl halides. In the lecture series, we have been discussing about the various reactions of alkyl halides like the substitution reactions, the SN1 and SN2 mechanisms involved therein, the factors affecting SN1 and SN2 reactions, the elimination reactions of alkyl halides, their E2 and E1 mechanisms, and the factors affecting E1 and E2 reactions. Taking the reactions of alkyl halides further, continuing our discussion on the reaction of alkyl halides, in the present lecture, we talk about the reduction of alkyl halides, the formation of organometallic compounds, the reaction of alkyl halides with sodium, the reaction with metal alloys, the polyhalogen compounds, and their properties. We introduce aryl halides in this lecture and talk about the structure of aryl halides, their nomenclature, properties and preparation. At the end of the lecture, we would sum up the lecture. The reactions of alkyl halides, we proceed to the reduction. Most alkyl halides react with zinc and aqueous acid to produce an alkene. This reaction is called as Frank-Land reaction. So, an alkyl halide reacts with HX in presence of zinc to form an alkane. For example, secondary butyl bromide gives N-butane. The catalytic reduction can be carried out with palladium charcoal and Raney nickel as catalyst. The reaction again produces alkanes. Reduction can also be carried out with lithium aluminum hydride or sodium borohydride. Then the reaction of alkyl halides with metals leads to many important reagents, like the reaction with magnesium gives rise to Grignard reagents, one of the very important reagents in organic synthesis. Grignard reagent is an organomagnesium halide which has a general formula RMgX, where X can be bromide, chloride or iodide. Here it is the carbon metal bond which is shown in case of ethyl magnesium bromide. It is generally prepared by the reaction between magnesium turnings and alkyl halide in dry alcohol free ether. The mechanism of formation of Grignard reagent follows a free radical mechanism which is not a chain reaction. So, the magnesium atoms of the metals abstract a halogen atom from the alkyl halide to form an alkyl radical first. Then the radicals combine to form the product. So, the alkyl radical combines with the magnesium bromide radical to give RMgBr. The reactivity order of alkyl halides used is that the alkyl iodide is most reactive, alkyl chloride being the least, and alkyl bromide has a middle reactivity. The primary, secondary and tertiary halides also form Grignard reagent, and as the number of alkyl groups increases, formation of Grignard reagents becomes difficult. If we look into the structure of Grignard reagent, we find that the carbon atom of the alkyl group is bonded covalently to magnesium, but is polar in nature, with carbon pulling electrons towards itself. The magnesium and halogen bond is ionic in nature. The alkyl group behaves like a carbon ion, which is a very strong base also and can deprotonate water, alcohol, carboxylic acid, etc. The general structure can be represented in this manner, where magnesium has a positive charge. This halide of course is negative, and the alkyl group can also be represented as an anion. The Grignard reagent can undergo a number of reactions to produce hydrocarbons, where it can react with an amine, an alcohol, water molecule or an acid. So, RMgX gets reduced on hydrolysis to yield an alkane. This is the general reaction of production of alkane, and As an example, this is secondary bromobutane, which gives an butane as the product. Alkyl halides react with lithium metal also and produce organolithium reagents. So, with lithium metal in a hydrocarbon solvent, these form alkyl lithium reagents. The alkyl lithium reacts with copper halide to form lithium dialkyl copper compound called the Gilman reagent. So, our lithium combines with copper halide and gives dialkyl copper lithium. The Gilman reagent, when heated with another alkyl halide, forms another hydrocarbon. So, if we take alkyl halide which has a different R group, it will give us the alkyl group from the Gilman reagent and one alkyl group from the alkyl halide. Alkyl halides react with another metal, that is sodium, and this reaction is called as Bot's reaction. An ethereal solution of alkyl halide, which could be bromide or iodide, react with sodium metal and produce higher alkanes. The reaction follows a free radical mechanism. So, if we take ethyl bromide reacted with sodium, we get ethyl radical. The two ethyl radicals combine to give a higher alkane. The alkyl halides can react with metallic alloys like sodium lead alloy and produce with ethyl chloride, they produce tetraethyl lead. Now, we consider some polyhalogens. The halogen derivatives of alkanes with more than one halogen atom present as the substituent are called as polyhalogens. They have a general IUPAC name as polyhalogenoalkanes. For example, di, tri and tetrahalogenoalkanes to name in general, and the important ones are haloforms like trichloro, tribromo and triiodomethane, named commonly as chloroform, bromoform and iodoform respectively. The dihalogenoalkanes can be of two types, gem or 1,1 dihalides, where the halogen atoms are attached to the same carbon. These can be prepared by the action of phosphorus pentahalides on aldehydes or ketones. So, ethanol combines with PCl5 and gives 1,1 dichloroethanol, or else by the addition of halogen acids to alkynes. So, ethyne combines with hydrobromic acid and gives bromoethane, which further reacts with HBr to give 1,1 dibromoethane. Dichloromethane is prepared by chlorination of methane, and the vicinal or 1,2 dihalides is another type of dihalogenoalkanes where the halogen atoms are attached to two different carbon atoms. These are prepared by the addition of halogens to alkenes. So, propene reacts with bromine to give 1,2-dibromopropane. The dihalogenoalkanes can be prepared by the partial reduction of haloforms. So, diiodomethane is prepared by reacting iodoform with sodium arsenide solution by the reaction shown here. The dehalogenation of 1,2 dihalides by zinc dust and methanol gives alkenes. So, 1,2 dibromopropane gives propene. This reaction can also be used to prepare 3 to 6 membered cyclic compounds. For example, 1,3-dibromopropane gives cyclopropane with zinc. So, this is 1,3-dibromopropane and this is cyclopropane. The trihalogenoalkanes can be prepared by the chlorination of methane in presence of nitrogen, and also the reaction between calcium hypochlorite or bleaching powder and ethanol or acetone. Ethanol forms trichloroacetaldehyde or chloral via the formation of acetaldehyde in the first step. So, this is the chloral which gets formed in first step. trichloroacetaldehyde finally forms the product in presence of hydroxide ions. This is the chloroform molecule. With acetone, trichloroacetone is formed in the first step, which gives chloroform in the next step. So, with acetone, again there is formation of trichloroacetone first, which gets converted into chloroform in the next step. The trihalogenoalkanes can also be prepared by the reaction of chloral hydrate or trichloroacetate with sodium hydroxide. This is chloral hydrate and this is trichloroacetic acid. With NaOH they produce the chloroform molecule. Tetrahalogenoalkanes can be prepared by chlorolysis, that is chlorination of heated chlorinated organic residues at a very high pressure. So, carbon tetrachloride can be prepared by this method, and tetrachloroethylene is formed as a byproduct in these reactions. Polyhalogens have got a number of uses, and as far their properties go, the dichloromethane and iodomethane are colorless liquids and used in a number of organic syntheses. Chloroform is a sweet smelling liquid which is slightly soluble in water but completely miscible in ethanol and ether, and it happens to be one of the first anesthetics used in earlier times. Bromoform resembles chloroform in properties and found in seawater, and also it is a metabolic product from algae. So, this is as far as the reactions of alkyl halides and the polyhalogens was concerned. In this lecture, we start with the aryl halides also. We introduce aryl halides and deal with the nomenclature of these aromatic compounds. Aryl halides have a halogen atom attached directly to the benzene ring. These are represented as ARX and also by the aryl group, for example phenyl in this case, and X is the halogen atom which is attached to it. The X can be fluorine, chlorine, bromine or iodine atom. These are named as haloarenes or halogenoarenes. For example, chlorobenzene, bromobenzene, etc. These are the structures of these two aryl halides. As far as the nomenclature of aryl halides is concerned, there can be only one halogen present in the benzene ring, or there can be more halogen atoms. If there is only one halogen atom bonded directly to benzene ring, it is numbered as one position and written as a prefix followed with benzene as main ring. So, for example, chlorobenzene, or we call it aryl chloride also. For dihalogen derivatives containing same type of halogens, the prefixes O, that is ortho, M, that is meta, and P, that is para, are used in common system. In IUPAC nomenclature of dihalogen derivatives, numerical prefixes 1, 2, 1, 3 or 1, 4 are used to assign the positions of dihalogen atoms. So, this is 1, 2 dibromo, that is ortho dibromobenzene, and this is 1, 3 dibromo derivative, this is 1, 4 or the para dibromobenzene. In the presence of two different halogen atoms attached to benzene ring, halogens are numbered alphabetically and written in the same way. For example, if there is one chloro group and a methyl group attached to the benzene ring, numbering will start from chlorine atom. If methyl benzene is written as toluene, then numbering starts from methyl group followed by the chloro group. Now, let us look into the properties of aryl halides. The properties of aryl halides are quite similar to those of haloalkanes. The CX bond is polar here also. The carbon halogen bond is shorter and stronger in haloarenes due to partial double bond character, and the resonance. Being attached to a sp2 carbon, the bond is less polar, as can be seen here. The dipole moment of this molecule clearly indicates. Due to less polar nature of aryl halides, they are insoluble in polar solvents like water, and they have high density as compared to water. Therefore, they form a separate lower layer in water. The force of attraction between water and aryl halide molecules are van der Waals dispersion forces, which are weaker than hydrogen bonds between the water molecules, hence the solubility. For the same aryl group, the melting point and boiling point increases with increasing the size of the halogen group, as is evident in this table. The size of the halogen atom is increasing from fluorine to iodine, and hence the boiling and the melting points. Direct halogenation of aromatic hydrocarbons is one of the methods of preparing aryl halides. So, transformation of ARH to ARX takes place where X can be a bromide or a chloride atom. The reagent used is normally the halogen, for example, X2, which could be bromine or chlorine, with a Lewis acid catalyst like ferric halide. It is a type of electrophilic substitution reaction. So, here we have benzene ring, which reacts with bromine in presence of iron catalyst and gives bromobenzene. The electrophilic species, in case of the preparation, the halonium ion, that is X plus, is formed by the removal of a halide ion by the Lewis acid catalyst. The active catalyst is not iron, but the ferric halide, which is formed by the reaction of iron with the halogen molecule. So, in this reaction, benzene is reacting with a chlorine molecule in presence of iron catalyst. We get the formation of dichlorobenzene molecule. One is ortho and another is para substituted product. The mechanism of electrophilic substitution follows the following steps. The first step is when bromine reacts with Lewis acid to form a complex, making it more electrophilic. In the next step, the pi electrons of the aromatic CC act as a nucleophile, attacking the Br and displacing iron tetrabromide. The cyclohexadienyl or benzenonium ion, the cation, is formed during the reaction, which is also called as Wieland intermediate. The aromaticity is lost in this particular step. So, formation of carbocation is the second step of this mechanism. In the third step, removal of the proton from the sp3 carbon bearing the bromo group takes place. Formation of a C double bond C and revival of aromaticity also takes place in this particular step. Generation of HBr and regeneration of the active catalyst takes place. So, in step 3, this bromide, which is attached to the catalyst, attacks and abstracts the proton from the cation, and in the next step, which is the faster step, bromine is replacing the hydrogen atom and the catalyst is regenerated, and also the aromaticity of the molecule of the benzene ring is regained. Decomposition of aryl diazonium salts is another method of preparing aryl halides. Diazonium salts are prepared starting from aromatic amines by diazotization reaction. Amines diazotize with sodium nitrite, hydrogen halide at very low temperature. The diazonium salts are unstable and are to be prepared in C2. So, during the reaction it has to be generated. NaNO2 with dilute HCl gives HNO2 and NaCl, and this is how, if we take aniline, it gets converted into the diazonium salt. Aryl diazonium salts can be converted into aryl halide in a number of ways. So, these are various methods wherein the copper halide like cuprous chloride or bromide, potassium iodide, or we can use a fluoro compound to get the substituted halosubstituted benzene molecules. Another reaction involving the diazonium salts is Sandmeyer reaction, which involves replacement by Cl or Br. So, diazonium salts are treated with cuprous chloride dissolved in hydrochloric acid or cuprous bromide dissolved in hydrobromic acid to form the respective haloarenes. All the three haloarenes, that is chloroarene, iodoarene and bromoarene, can be prepared by this method and by the reaction which is shown here. The diazonium ion in presence of cuprous chloride and HCl gives chlorobenzene. Sandmeyer reaction also involves aryl iodide preparation by simply heating with aqueous solution of potassium iodide. So, diazonium chloride reacts with potassium iodide aqueous solution to give iodobenzene. Gattermann reaction is another way of preparing the aryl halides, where diazonium salt is simply warmed with copper powder when it gives the substituted toluene. In this case, chloro-substituted toluene is obtained. Another reaction is Schimann reaction, which involves replacement by fluoro group, where addition of fluoroboric acid to the diazonium salt gives insoluble diazonium fluoroborate, which on gentle heating gives the fluoro compound. So, this is the sequence of reaction which is followed. The diazonium salt will react with the fluoroboric acid, and which in further steps forms the fluorobenzene molecule. There is another reaction, Bals-Schimann reaction, which involves the aryl diazonium salts for the preparation of fluorobenzene by using fluoroborate salts. Benzene diazonium tetrafluoroborate can be prepared by diazotization of aniline with sodium nitrite and fluoroboric acid at 273 to 278 K temperature. Aniline can be treated with sodium nitrate and the fluoroboric acid to give diazonium salt with fluoroborate complex, which further gives rise to the formation of fluoro derivative. There is another process called Rasching process, where chlorobenzene is prepared commercially. A mixture of benzene vapor, air and hydrogen chloride is passed over copper chloride to produce chlorobenzene. The silver salt of aromatic acids with bromine react to give aryl bromides. So, this is basically silver benzoate which reacts with bromine to give bromobenzene. Aromatic hydroxy compounds react with PCl5 and form aryl chlorides when hydroxy compound has electron attracting groups. Let us sum up the lecture. In this particular lecture, we started with the reaction of alkyl halides, wherein the reduction of alkyl halides was taken up. Also, the formation of organometallic compounds with magnesium and lithium. The reaction of alkyl halides with sodium, which is called as Wurtz reaction, was also discussed. The reaction with metal alloys leads to compounds like tetraethyl lead. The polyhalogen compounds which contain more than one halogen atom have also been discussed in this lecture, where the preparation of di, tri and tetrahalogenoalkanes was discussed, and also the properties and uses of these particular compounds. We started with the aryl halides, introduced the structure of aryl halides, talked about the nomenclature of aryl halides, the properties and some of the methods of preparation of aryl halides. We will continue our discussion on aryl halides in our next lecture when we will talk about their reactions. Thank you.